Right now, something is moving through the ocean floor that nobody can stop. A pulse of energy, invisible, silent, traveling southward through thousands of kilometers of solid rock toward one of the most densely populated coastlines in the southern hemisphere. And at the exact same moment, on the opposite side of the Pacific Ocean, a fault that has been completely locked for 326 years just woke up in a way that has monitoring stations lighting up across the entire Pacific Northwest. I am going to show you exactly what is happening, what it means for real people in real cities, and why the final piece of this puzzle is the part that nobody in mainstream science is comfortable talking about out loud. But I am not going to give you that piece until the very end of this video, because to understand it, you need to understand everything that came before it. Before we go any further, drop a comment right now and tell me where you are watching this from and what time it is there. I want to know how far across the world this story is reaching tonight. Now rewind with me, because this story does not start with a pulse or a locked fault or a coastline at risk. It starts with a single morning, a single moment when the floor of the Pacific Ocean broke. On the morning of March 24th, a magnitude 7.5 earthquake struck deep beneath the Tonga segment of one of the most violent collision boundaries on this planet. To put that in perspective, a 7.5 releases energy roughly equivalent to 32 million tons of TNT. That is not a tremor. That is a full boundary rupture on a fault where the Pacific Plate is physically diving beneath the Australian Plate at nearly double the speed your fingernails grow. Now here is what should have happened next. A burst of aftershocks clustering tightly around the rupture zone, smaller earthquakes fanning outward, getting less frequent over time, following a statistical decay pattern that seismologists have trusted for over a century. The system exhales, the tension drops, things calm down. That pattern is so reliable it has a name. It has been holding for 130 years of earthquake science. Except this time, the aftershock cloud never appeared. The energy from a 32 million ton equivalent rupture simply did not show up where it was supposed to, and if you have spent your career studying fault systems, that is not a curiosity. That is a question with only one answer. The energy went somewhere else. Days later, monitoring networks started detecting exactly where. Not scattered outward in all directions, not clustered near the original rupture, but moving south, step by step, event by event, each one farther south than the last, each one sitting along the same fault corridor, following the same structural geometry, separated by days rather than hours. This is not how aftershocks behave. Aftershocks scatter. What was happening here was different. Each event was adjusting to the stress left behind by the event before it. The fault was not releasing energy, it was transferring it, like a baton passed from runner to runner in a relay race that runs directly toward New Zealand. Scientists have a name for this process too, Coulomb stress transfer, and it is one of the most important ideas in understanding how fault systems actually communicate. When one segment of a connected fault ruptures, it does not just release local stress, it rearranges the entire stress field around it. Some neighboring segments get pushed closer to their own failure point, some get pushed further away. And in a system as long and continuously connected as the Tonga to Kermadec to Hikurangi corridor, that rearrangement can travel over enormous distances, segment by segment, like a slow-motion chain reaction that does not need a single massive event to keep moving. We have seen this exact pattern before. After the 2004 Sumatra earthquake, a magnitude 9.1, the adjacent segment to the south broke 3 months later in a magnitude 8.6. That was not coincidence. That was Coulomb stress transfer activating a neighboring locked patch that had been pushed past its threshold by the first event. The Kermadec swarm is smaller in scale, but the geometry is the same, and the direction it is traveling points directly at the Hikurangi subduction zone, the fault system sitting off the east coast of New Zealand's North Island, a margin capable of producing a magnitude 8 to magnitude 9 earthquake, a fault with its own centuries of accumulated strain, a coast with 5 million people on it. Now here is where this story stops being about one region and becomes something that demands a completely different kind of attention. Because at the exact same time that this stress migration was unfolding in the southwestern Pacific, something happened 10,000 kilometers away, on the opposite side of the ocean, that no single fault story can explain. The Cascadia subduction zone recorded 791 tremor events in a single day. Not over a week, not scattered across a month, in one day. These are not earthquakes you would feel. They happen between 25 and 45 kilometers below the surface, in a zone where rock behaves differently than it does near the top, where fluids released from the subducting plate reduce friction enough to allow slow, episodic sliding. The surface above you gives no indication anything is happening. Your walls do not shake, your windows do not rattle. The ground feels completely stable.
And that is exactly what makes this signal so significant. Because what is actually happening below is a loading mechanism. Every time that deep zone slips, even slowly, even silently, it transfers a small increment of stress upward into the locked zone above it, into the part of the fault that has been holding everything in place since the year 1700. 326 years of continuous plate convergence. An estimated 10 meters or more of potential slip stored in that locked interface, waiting. The tremor events are not the danger. They are the signal of a process that has been feeding stress into a locked zone for decades, cycle after cycle, adding to 3 centuries of accumulation that was already there before any of these tremor cycles ever began. 791 events in a single day, both the northern and southern segments showing activity at the same time. That is not a routine cycle. That is a system-wide pulse. Now hold both of these facts in your mind simultaneously. The Kermadec system is redistributing stress laterally, moving horizontally along a connected arc toward a populated coastline. The Cascadia system is redistributing stress vertically, pushing upward from a sliding zone into a locked zone that has been absorbing strain for over 3 centuries. 2 different fault systems, 2 different directions, 2 different mechanical regimes, 10,000 kilometers apart, active in the same week. There is no established physical mechanism that directly connects these 2 systems. They sit on different plate boundaries. They are driven by different tectonic configurations. A rupture in Tonga does not pull on a fault in Oregon the way 2 ends of a rope pull on each other. The plates do not share a loading mechanism. And yet, the timing sits there, refusing to be ignored.
Here is where we need to be careful and honest, because this is the part of the story where the science ends and the uncertainty begins. And how you sit with that uncertainty is going to determine whether you come away from this video with useful information or with fear that has nowhere to go. There is a third signal. It arrived while both fault systems were already showing these stress indicators. A geomagnetic storm hit Earth. Not a dramatic one by historical standards, a KP index of 7. Strong enough to push auroras down to latitudes as low as 30 degrees. Strong enough to generate measurable electrical currents flowing through the crust itself, arriving at the precise moment when 2 of the most dangerous subduction zones in the world were in active states of internal stress redistribution. Now I need to tell you what mainstream science says about this, and then I need to tell you what mainstream science is uncomfortable saying about it. The official position is clear. Geomagnetic storms do not cause earthquakes. The energy deposited by even a significant solar storm is orders of magnitude smaller than the energy stored in a tectonically loaded fault. The idea that a solar wind gust could trigger a magnitude 8 is like suggesting that breathing on a dam could cause it to burst. The proportions simply do not work. But there is a smaller, more specific question that some researchers have been quietly studying for years. Not whether the sun causes earthquakes, but whether a tiny external perturbation could influence the precise timing of a rupture on a fault that is already at the very edge of failure. A fault that is going to break anyway,
in days or weeks or months, regardless of anything the sun does. Could that infinitely small additional nudge determine exactly when the first patch of the locked zone reaches its local failure stress and begins the chain reaction we call a great earthquake? This is called marginal triggering, and the honest answer is that we do not know. Some peer-reviewed studies have found weak but statistically detectable correlations between geomagnetic activity and elevated earthquake rates in the days that follow. Others have found nothing. The results depend on methodology, on which catalogs are used, on how geomagnetically active a period is defined. No study has demonstrated a reliable predictive relationship. No mainstream seismological organization incorporates solar activity into hazard models. But the research has not been definitively closed either, because the researchers pursuing it are not fringe figures. The papers have passed peer review. The correlations keep appearing in different datasets examined by different groups. And there is a physical environment where this hypothesis is at least mechanically plausible. The deep transition zone of a subduction fault, where high-pressure fluids reduce friction to the point where the interface is balanced on a knife edge between stable and unstable sliding, is exactly the kind of environment where tiny perturbations could theoretically matter, not as a cause, but as a final increment in a system that was already there. So here is what we are actually looking at. 2 megathrust subduction systems showing internal stress redistribution at the same time, a geomagnetic storm arriving in that window, a ring of fire that has been collectively more active in recent weeks than any average period, and 326 years of accumulated strain on a fault whose last rupture, on January 26, 1700, we know happened with unusual precision because a tsunami crossed the entire Pacific Ocean and struck the coast of Japan, where historical records documented flooding without any local earthquake to explain it. Is something about to happen? The honest scientific answer is that we do not know. And anyone who tells you they do is not giving you science. They are giving you a story that feels more manageable than the truth. The truth is that neither of these fault systems needs a geomagnetic storm to be dangerous. They were dangerous before this week, they will be dangerous next year. The Cascadia megathrust is the most dangerous seismic structure in North America on its own terms, loaded by its own physics, on a timeline that is measured not in days, but in geological certainty. The Hikurangi margin has produced catastrophic earthquakes before, and it will produce them again. What these signals give us is not a prediction. What they give us is a reminder that we are watching 2 of the most consequential fault systems on this planet in states of active internal motion, that the processes driving them toward their eventual failures are not paused, that the locked zones are still holding, as they have held through hundreds of previous loading cycles, by a margin we cannot measure and cannot see. And somewhere in that invisible margin, the plates keep moving, the strain keeps accumulating, the fault does not know what year it is, it does not have a timer, it responds to stress, and the stress has not stopped building. The Earth is not waiting, we are. And the distance between where these faults are now and where they will be when they finally move is shrinking by a few centimeters every single year, silently, certainly, whether anyone is watching the screens or not. That is what these signals mean, not a countdown, not a warning, a reminder that the most dangerous things on this planet do not announce themselves, they just arrive. Stay informed, stay prepared, and if you want to understand what full Cascadia rupture preparedness actually looks like for the cities in its path, leave that in the comments and I will cover it next.